So in Lesson 7's homework on symmetry, we're going to spend some time talking about the three different types: line, point, and rotational. So if we look at each letter, A, I see a vertical line of symmetry. A does not look the same upside down, so therefore it's not going to have point. And there's no number of degrees short of 360 that is going to be rotational symmetry. If we look at the letter B also has a horizontal line of symmetry. If you look at it upside down, it does not look the same, and there is no amount of degrees you could rotate the letter C in order to have rotational symmetry. The letter C also has a horizontal line of symmetry, but the same thing, it does not look the same upside down as it does right side up, so not point, and there's no number of degrees rotationally that you could rotate it. The letter D also has line symmetry, horizontal, does not look the same upside down as it does right side up, and there's no number of degrees. E, well, there's that horizontal line symmetry again. It does not look the same right side up, upside down, and there's no number of degrees. M has a vertical line of symmetry. There's no number of degrees, and it does not look the same upside down. So far we've had the first 6 have just been line symmetry. N, I do not see any line symmetry in N. However, if you look at the letter N upside down, it does have point symmetry, which means it has rotational symmetry. For the letter O has line. It looks the same upside down, so it's got point. And since it has point, it has rotational symmetry. The letter P has none. There are no lines of symmetry. It does not look the same upside down, and there are no number of degrees that you could rotate P to have it look the same. Z has no lines of symmetry. However, it does look the same upside down, and it does have rotational symmetry. So you can see through this that it's much easier for something to have line symmetry than it is to have point or rotational symmetry. Use figure 1 to answer problems 1 and 2. Draw all lines of symmetry, and you're going to locate the center of rotational symmetry. So when this is a regular pentagon, all of your lines of symmetry are from, and actually I'm going to use my straight line tool here. All of your lines of symmetry are from your vertex through the midpoint of your opposite side. So I'm just kind of guesstimating here where all of those mid segments are. Remember, 5 sides, so 5 lines of symmetry. And that's going to make our center of rotational symmetry that point where they all intersect. So there's our center of rotation. So we want to describe everything that it has. Well, it's got line symmetry. We just drew them all in. And it has rotational symmetry. It does not have point symmetry because it does not look the same upside down. How many rotations are there? Well, there are the same number of rotations that there are sides. You have 5, and how many reflections? You also have 5. So 5 lines of symmetry, 5 rotational symmetries. Which diagram shows a dotted line that is not a line of symmetry? Okay, and the one that shows something that is not is 4. If you reflect all those curved pieces over, they do not end up on top of their corresponding curved pieces, wherein number 1, the hexagon will just trade places, number 2, the trapezoid will just trade places, and number 3, the square, they will just trade places. They'll end up perfectly on top of each other. How many lines of symmetry does the accompanying figure have? An infinite number. We have 2 lines of symmetry, 4 lines of symmetry, and 6 lines of symmetry. Well, I definitely see 1 vertical and 1 horizontal line of symmetry. Now, if we were to draw our diagonal lines of symmetry as well, since this is balanced on all sides, okay, those would line up perfectly with each other, and those are the only ones that I see. So therefore, how many lines of symmetry are we going to have? We're going to have 4. Draw all the lines of symmetry in the accompanying diagram. Well, you should have this one vertical line of symmetry. Straighten that out a little bit so it actually ends up in the middle. You have a horizontal line of symmetry. And those are going to be our only 2 lines of symmetry for this problem. Determine the minimum number of degrees needed to rotate a regular decagon. So that's 10 sides onto itself. So whenever we're trying to figure out how many degrees of rotation we need, we're always going to take 360 and divide it by n, where n is our number of sides. So in this case, 360 divided by 10 gives us 36. So the minimum number of degrees is 36. Sometimes multiple choice questions say, what is a number of degrees? So in that case, we would do any multiple of 36 would be a degree of rotation for a decagon. But if it says minimum, we got to go with that first one of 36.